So hello and welcome to the first Tech Extra for 2021. The title of this talk is Characterizing Network Paths in and out of the clouds. My name is Igor Sfiligoi. I come from the University of California, San Diego Supercomputer Center. Again, a reminder that this event is being recorded and it will be posted along with my slides at the Internet 2 Tech Extra website. Please hold any questions until the end of the talk, but post them in the Q&A anytime you want. We'll go over those at the end. The chat session, it's mostly meant for group discussion between participants and will not be monitored by me or the panelists. That should be the Q&A. So thank you for joining us, and we are ready to begin. So I said, this is characterizing network paths in and out of the clouds. But before we go into the talk itself, let me just spend a word about myself. I have been working with distributed computing for over 20 years. I started in real-time data acquisition and then moved to more general on-site compute clusters. Then the grid computing came around and have spent quite a few years there. Did some traditional HPC work, tightly integrated, InfiniBand, stuff like that. And lately, I have been doing more cloud, although I still do occasionally pretty much everything above, depending on the project I work on. Geographically, I started in Italy. I moved to the US Midwest and then ended in San Diego, which is in California, if anybody doesn't know that, where I'm still now. I'm currently working as part of the San Diego Supercomputer Center. I'm deeply involved with the Pacific Research Platform and Open Science Grid teams. And I work with many different kinds of scientists spanning astrophysics, microbiome, fusion, high energy physics, and possibly others. Most of my background is in research or academic environment, but I did a few years in industry too. So you see, I have done a little bit of everything along the years. Now, this talk is all about cloud computing. And I'm sure you recognize that cloud computing is pretty normal these days. It's hard to look anywhere and not see the cloud mentioned. I have here a few snapshots from various websites that span the wide spectrum of communities. And just to show that, yes, cloud is everywhere these days. So it's not exotic by any stretch of imagination where. But most of the time you hear people talk about cloud, it's talking about cloud computing. And what they mean with that is really distributed computing, because really nobody cares about a single machine anymore. It's all about ensembles of machines. And when you have ensembles of machines, a network starts to play a really important role, especially in scientific computing. And the two things that typically network would do would move input data in and then deliver outputs to permanent storage or some other location. So networking is really important, because if networking is low, all that compute is really wasted, because all you do is wait for data, and that's not something you want to do. Unfortunately, looking around, I couldn't find very much information about cloud networking. It's all about compute. Very little information was available about cloud networking. And that was a problem, because I was supporting IceCube, who was planning a large cloud burst. And when you talk about cloud burst, you mean a large spike in compute power. But to feed that compute power, you also need a large spike in networking. Not having much information available, we were not really sure if what we were trying to do was actually feasible. Of course, we knew that networking was there and the data would eventually arrive, but we didn't want to waste a lot of compute cycles just waiting for the data to arrive or being staged back. So we decided that we wanted to do some research on our own. So we went ahead and measured what was possible on our own. So how do you go about measuring the cloud networking? Well, there is one thing that is really nice, is that all cloud providers operate large pools of distributed object storage. And These pools are very scalable and are guaranteed to be separate from compute capacity by design. So they end up being a really great endpoint for data movement benchmarking. So we uploaded a bunch of data in there. And then we went ahead and provisioned compute nodes, which is something the cloud is famous for. And if you look around, you'll see that most instances come with 10 gigabit per second NICs or better. So that was not the question. The question was, can the network backbone actually scale as you add more nodes with high data needs? But provisioning, it's easy. The only potential trick in the cloud is ensuring that you can actually run all the tests in parallel, because as I said, we want to measure the backbone, not the single node. So all the tests must run at the same time and create contention on the backbone. For scheduling our test jobs, we use Condor, mostly because I'm very familiar with it. I use it for many years, but probably any modern batch system would have done just as fine. So I started within a single cloud region. You can think it logically as being a data center, although probably it's a couple of data centers, but it's more or less a local area network. And I started increasing the number of compute clients who try to maximize the use of local area network links. And you see it scales. We went to about 1.5 terabit per second, and then we stopped. We didn't really hit any walls, but that was more than we needed. So we said, okay, the networking inside the single cloud region is plentiful, and writing to the cloud storage can be done at high speed. So we are good here. But the cloud is nice because you can get resources from all over the world. You're not limited to a single location. So you definitely want to measure what is possible when moving data between cloud regions. And you can do exactly the same identical setup because cloud object storage is accessible from anywhere. So it's great for wider network benchmarking too. So we uploaded the data to a few more storage locations in the cloud, and then provisioned compute resources just in other regions so that they were not collocated to where the data were. A nice thing about doing that is that you can move data that is guaranteed to stay inside cloud provider operated networking. So you don't have any artificial bottleneck. It's whatever the cloud can deliver. And here are the results. Inside the US, going from east to west, west was between Oregon and Washington, depending which cloud provider you're talking, and the East Coast is all around the Washington area. And you see, Google is able to deliver terabit per second speeds, even over a wide area network. AWS was a little lower at 400 something, and Azure even less at around 200. But that was still more than we needed. By the way, this was done 2 years ago. We haven't done it since, so it may have changed, but if anything changes for the better, not for the worse. And when you look at international, you see that the US-Europe link must be very important to them because you get virtually the same performance numbers going from US East Coast to places in Europe, while Asia is a little worse connected, at least for AWS and Azure, which were around 100 gigabit per second. Google stayed at almost gigabit per second, even going there. So definitely for what we've seen, Google has the best networking, or at least had 2 years ago. Now, knowing how fast you can move data inside the clouds is nice, but at the end of the day, we want to get the data in and out of the clouds. And assuming that all the communication is symmetric, the easiest way to do it is just do the same as we did before. Keep the cloud object storage as a data endpoint, because we know that can scale pretty much to infinity, and just get some execute nodes outside the cloud. It's actually easier to get a lot of small compute nodes outside the cloud that getting really performance storage there. The challenge is just where do you get them? Because if you put them in a single location, the border wide area network link out to the campus will likely be the bottleneck. Instead, we really wanted to see what the backbone is capable of. And I happen to have access to the PRP Kubernetes distributed cluster, which has nodes all over California, actually even beyond, but I limited myself to California. And they look like as they were all co-located from workload management system point of view. So I just provisioned a bunch of them spanning as many sites as I could, and then ran the tests, pretty much identical to the ones I did before. And here you have a snapshot of what I see. 100 gigabit per second, it's looked like what you could do last winter. And Azure was a little better than the other two, but not by a large factor. So that was plentiful for us. So we didn't investigate further. But yeah, for most application, it should be sufficient. Now that we did all the tests and convinced ourselves that networking was not the limit, we went ahead and did the cloud bursts, and they went flawlessly. There were no network-related issues that we could observe, and we measured the compute capabilities of the cloud the way we wanted to. By the way, we will have a talk about this in a month or so in this forum too, so I'll not spend any more time on it. Now, so far, all I talked about was capabilities, but anytime you talk cloud, you must talk cost too, because everything or almost everything in the cloud is mattered and you have to pay for. And that's definitely is the case for getting data out of the cloud. By the way, getting data into the cloud is free. There's their business model. Import as much as you want in us, but never try to leave the data out of us, because you will pay dearly for it. Here you see one of the tests I ran. It cost me almost $2,000 to do it. And you see the cost for the compute was pretty much negligible. It's all about data transfer. And that's not surprising, because you paid about $80 per terabyte to move data out of the clouds. And we know that a terabyte is not a large amount of data. So when you have data intensive applications, that can get really expensive. Now, I should point out that for the first two IceCube cloud runs, that was not a problem, because we decided to go with compute intensive simulation applications, because we really were not interested in exercising the networking. As I said, we started with the assumption that networking could be a problem, although at the end it was not. But having compute intensive simulation means not that much data is being moved around, so the network costs were negligible. It was not a big deal. Actually, I think we didn't pay anything, because you get the 15% cost forgiveness in the clouds. But if you want to go data intensive, and IceCube does have some data intensive simulations, those produce about 10 times the output data per flops of compute than the ones we used in the first two cloud runs. And you put the numbers in the cost estimator, you see that if you use the most cost-effective GPUs, it costs about 12 cents to run a job. But getting the outputs back to on-prem costs you 16 cents. So the network cost can be more expensive than compute costs. And that's not something you would want to see. If you have to, you will pay, but it's definitely not something you would want to see. So we looked around if there were any alternatives, and indeed there are. All major cloud providers have option to provision dedicated network links, and Internet too can act as a link to our on-prem research networks. They brand it as Internet to Cloud Connect. You have the link there if you want to look for yourself what it does. But the point is that once you provision a dedicated link, you can use it and you get a deep per gigabyte discount of per terabyte if you want, because we're really talking about terabytes. But on the flip side, it comes with a fixed per hour cost and fixed max throughput. Here I have a summary table, which shows that if you do nothing and just go the standard route, you pay the $80 per terabyte. You have no limits of how fast things will go, best effort, and we show it can go above 100 gigabits per second. But if you use dedicated links, that cost goes down to about $20 per terabyte. But you have very specific max throughput that can go through. It's essentially traffic shaping. And you pay a certain amount of money per hour if you use that link or not. As long as it's provisioned to you, you keep paying for it. And the ranges are simply because different cloud providers have different pricing structures. I will not go into the detail. You can look it up on their websites. Now, knowing that we can do it, we decided to actually go ahead and do it, because, as I said, we wanted to do some data-intensive simulations. We wanted to do it in the cloud, so let's do it and try to save money by getting dedicated links. Now, the problem was that IceCube wanted more than 100 gigabits per second to a combination of UW-Madison and UCSD. But at least last fall, Internet 2 did not have any links that could exceed 10 gigabits per second into any of the cloud regions. And you have to have one link per cloud region too, at least one. And 10 gigabits per second was really the best case. Most were 5 gigabits per second or less. So in the end, we had to stitch together over 20 links. And you see the list here. It's not very important, but you see that there are a lot of them. So when you have a lot of links to manage, well, it gets complicated fast. And it turns out that it's not just a procedural thing. It's actually human intensive because it requires many parties to actually execute it. And this is because the final user cannot provision a dedicated link on its own. It's not like with the compute. You get to the cloud portal, you request a VM, and boom, it's yours. That's all. Very easy. No questions asked. Just provide your credit card or whatever. To provision a link, it's way more complicated because it involves the user actually going to the cloud and doing something. You need an intermediate cloud provider that bridges the cloud and on-prem networks. And in our case, it was Internet 2. And then you need the local on-prem networking team, one for each location you want the traffic to go. And in our case, we had two. There was one at UCSD and one at UW-Madison. And what does the on-prem networking team need to do? Well, for one, it has to provision the IP address pool that you will assign to the cloud compute VMs. Yes, the VMs look like as they belong to the on-prem campus. All the IPs are must be part of the IP campus. You're not using the IP addresses provisioned by the cloud. So whatever you pick will go to that site, and then they also must establish level 3 VPN to the Internet 2 peering points in order for the routing to actually work. Because of course now the IP look like they are inside the campus, but they are really somewhere else in the world. Could be on the other side of the world. We had things in Europe that were routing to UW-Madison, for example. Once you have that, you just need to connect the dots through Internet 2 and the cloud provider. As you can imagine, when you have multiple people that have to talk together, the human interaction plays a significant role. It's very hard to completely automate. You will spend a lot of time just back and forth coordinating stuff. The silver lining is that this is only really needed during link setup and tear down. Then the rest of the time it just works and nobody needs to be involved. But since you're paying per hour, you probably don't want to keep them up unless you need them. So establishing and tearing down those connections may be something you want to do more often than you want, because it's relatively expensive. The other thing you will find when you go the dedicated cloud route, especially in compute intensive or data intensive applications, is that having a max limit that you're paying for, it's hard to keep busy, because most compute jobs will not stream their data, definitely not for IceCube, which was pretty much the extreme, because a single job would run for like 20-25 minutes, produce a big file, and then want it shipped back to an on-prem storage in a matter of seconds. So if you want to keep the links full but not overload it, you cannot just let it to chance how things work, because you will either end up in the upper situation where everything works fine, but you have a lot of unused capacity that you are paying for hourly, or worse, you actually use all the capacity, but then the jobs are just waiting there, wasting the compute resources because files need to be moved and there is no network capacity, which is something we wanted to avoid to start with. By the way, this was done as a test run to really see how bad the worst case scenario was. So we definitely need compute workload shaping. And there are several techniques. In our case, the easiest one turned to be to just slowly ramp up, so that startup time and thus the end times were spaced enough that all of this gets randomized. So you can stay at around 80-90% utilization on average and have very few network congestion peaks and very few deep underutilized links. So it is a little bit of work, but can be done. We showed it. We ran for about a day, or most of a day, and delivered about, produced and delivered about 130 terabytes of data back to a combination of UCSD and UW-Madison. By the way, it took about 200 petaflop hours of GPU compute to get there. And this $5,500 is actually a good deal, because if you put the numbers in the list price, you see that 100 terabytes should have cost about $11,000. So we actually saved half of it. And I would say $5,000 is not spare change. So even if it takes FTA day of a person to do it, it still pays off with dividends. So it definitely showed economic value for us. And I would point out that this could be easily further optimized, because in our case, we are trying to do something that we haven't heard of anybody else before doing it. So we were very, very conservative. We provisioned all the links way ahead of time, make sure everything worked before starting the run. And then after we were done, we make sure everything was where it needed to be before shutting them down. So probably the links were used a quarter of the time. And this $5,500, really half of that went into hourly lease fees. So if we were really aggressive and try to bring up the links and shut them down exactly at the optimal time, this could probably be more like 3,000. We didn't try to be that aggressive. We thought that was already a pretty good success. And here, just to show that even though we paid less, we still were able to maximize the use of our on-prem resources. This is a snapshot of the UW-Madison wide area network link monitoring. And you see that for a couple of hours, we were in the 80-90% range, which is pretty much the most a campus would allow you before shutting you down as a denial of service attack. So I think we did pretty good there. And we were quite happy with what we achieved. And this is pretty much all I have. Just to summarize, there is plenty of network capacity in the clouds. We saw terabits inside a single region, between several hundred gigabits to a terabit going across wide area network when staying inside the clouds. So that should be sufficient for virtually any workload I can think of. Now, getting data in and out of the clouds, it's a little slower, but still pretty fast. We see 100 gigabits per second to be pretty normal. And it is likely that you will end up hitting campus boundary link bottlenecks way before you will hit limits in the cloud connectivity. Just be aware that cloud networking cost can be an issue because at $80 per terabyte, it doesn't take a lot of data to rake up a large bill. And here, if you are expecting a lot of data being moved around, definitely consider dedicated links and internet to Cloud Connect. It's an obvious route there. But make sure you keep them busy because the hourly fees can fast rake up. So a day of hourly fees, it's several terabytes of data, worth of terabytes of data. So think about that. I finally would like to acknowledge that this was paid by the National Science Foundation through these grants, and I really appreciate and thank them for that. And this is really all I have. So thank you for attending this presentation. Again, just a reminder, this event was recorded and will be posted along with my slides, the Internet to Tech Extra website. So if you have any questions, make sure they're all posted. And I will also make sure you fill out the survey. Thank you. So I'm ready for questions.
All right, so it looks like we have had one question submitted so far. Says, my understanding from cloud providers is that they are willing to discuss raising the limits on egress fee waivers in specific situations where the limits present problems to legitimate use. Do you talk to the providers about that?
No, we didn't. We wanted to see what was possible without going through legal. So yes, there is a lot of stuff that can be done through sales people and legal, but they will only talk to you if the bill is in the hundreds of thousands of dollars. Anything less than that, you are small fry. So yes, if you expect a couple $1 million for cloud bill, they will definitely talk to you because they want you to spend $500,000. Is better than you going away somewhere else. But unless you are that big, I had a few chats in other contexts discussing what could we do to get stuff, and every time was, are you spending at least $100,000 a month? No, okay, bye. This is a route that you can take anytime, no legal or salespeople involved.
All right, thank you. And it looks like that is all we have for questions, so appreciate your time.
So yeah, if there are no other questions, thank you very much. I hope you learned something interesting from this. And yeah, apart from the cost, the clouds are very nice platform to work with.